Your Spark job died with an out-of-memory error. You doubled the memory, it died again. This is one of the most demoralizing experiences in working with Spark, and it happens because the error name is misleading. Out-of-memory error almost never means you do not have enough total memory. It almost always means one specific thing ran out of room. And doubling total memory does not fix a problem that lives in one task. Today, we are going to build a precise map of where memory goes in Spark, what spilling is and why it is normal, and a taxonomy of the 4 ways a job dies with a memory error, each with a different cause and a different fix. Start with the map. Every executor has a fixed amount of memory, and Spark divides it into 2 main regions. The first is execution memory. This is the working space for active computation. When a task needs to build a hash table for a join, sort a partition, or hold intermediate results during an aggregation, it draws from execution memory. This is the memory that gets used and released as tasks run. The second is storage memory. This is where cached data lives. When you call cache on a dataset, it goes here. Broadcast variables also live here. The boundary between these 2 regions is not fixed. By default, Spark uses a unified memory model where execution and storage share a pool, and each can borrow from the other when the other is not using its space. Execution memory can expand into unused storage space, and storage memory can expand into unused execution. But there is an asymmetry worth knowing. If execution memory needs to expand and storage memory is in use, it can force some cached data to be evicted. Evicted cache blocks are not permanently lost. They get recomputed from lineage on next access, which is slower than reading from cache, but not a failure. The reverse is not true. If storage memory needs to expand and execution is in the middle of computation, it cannot evict execution data. Storage has to wait or give up. This matters because it means caching a large dataset can silently steal memory that tasks were counting on, which causes more spilling, which is the next thing to understand. Spilling is what happens when execution memory runs out for a task and that task still has work to do. Spark writes the data it cannot hold in memory out to a temporary file on local disk, frees the memory, continues, and reads it back later when needed. Spilling is not a failure, it is the designed fallback. A job that spills is slower than one that does not, but it still produces the correct answer. The concern is when spilling is so severe that the job slows to a crawl, or when spilling is itself so large that it fills the local disk. Now the taxonomy. 4 ways a Spark job dies with a memory error, and they are not the same problem. Failure 1. Driver out of memory. The driver is running your program and coordinating your job, but remember from episode 1 that it should never hold your data. If it does, it is because you called collect, or something that behaves like collect, and pulled the entire result back to a single process that was not sized to hold it. The fix is almost never to give the driver more memory. The fix is to stop collecting. Write the result to storage instead. If you genuinely need a sample, take a small one explicitly rather than materializing the whole thing and then slicing it. Failure 2. Executor out of memory from skew. We met skew in episode 7. One partition holds a much larger share of the data than the others. The task processing that partition is doing much more work, building much larger in-memory structures than the tasks on other partitions. Those other tasks finished fine. This one ran out of room. The error looks identical to any other out-of-memory error, which is why the skew section of the Spark UI is the first place to look when an executor dies unexpectedly. If the task that died was processing a partition 10 times larger than the median, that is your answer, and the fix is from episode 7. Failure 3. Executor out of memory from a single large partition. Different from skew in an important way. Skew means one key is disproportionately common. A single large partition can happen even with perfectly even key distribution simply because you have too few partitions and each one is too large. If your job starts with 100 partitions instead of 3,200, each partition holds 40 times more data. If the memory task is sized for the partition count you should have, it will not hold the partition count you actually have. The fix is to increase the number of partitions. For shuffle stages, the relevant setting is spark.sql.shuffle.partitions, which defaults to 200 and is often too low for large datasets. You can also repartition explicitly before the operation that is dying. This is one of the most common memory errors and one of the easiest to fix once you know where to look. Failure 4.
Executor out of memory from garbage collection pressure. This one is different in character. The job is not holding a single enormous object. It is creating and discarding many medium-sized objects, and the Java garbage collector cannot keep up. Memory fills with objects that should have been collected, the process runs out of heap space, and the job dies. This pattern tends to appear with user-defined functions, especially ones that create new objects on every row, or with code that accumulates results in a loop, rather than letting Spark handle the distribution. The diagnostic sign is a job that gets progressively slower rather than failing cleanly at a consistent point. The fix is usually to rewrite the offending code to use Spark's native operations where possible, which operate on optimized internal representations rather than Java objects, or to reduce object creation inside user-defined functions. So here is the diagnostic flow, because the fix depends entirely on which of these four you have. First, check whether the driver died or an executor died. Driver death with a memory error almost always means a collect call. Executor death needs more investigation. Second, open the Spark UI and go to the Stages tab. Look at the task size distribution. If one task was processing a partition much larger than the median, you have skew or a partition count problem. Skew shows a hotkey. Partition count shows uniformly large partitions. Third, look at spill metrics. Spill bytes are shown in the stage detail. If you see enormous spill, you have a memory pressure problem that is survivable but expensive. Reducing partition size will help. Fourth, if the job gets progressively slower without a clean failure and task sizes look reasonable, check for garbage collection. The executor logs will show GC pauses accumulating. One honest note before the summary. Memory configuration in Spark has many knobs, and tuning them is genuinely complex. The fraction that execution memory occupies, the fraction that storage can claim, the overhead reserved outside these pools, all of it is configurable. The right values depend on your workload, your cluster, and your data. The point of this episode is not to give you the right numbers. It is to give you the right mental model. Once you know which failure you have, the configuration changes that make sense become obvious rather than arbitrary. Next time, the file format underneath all of this, why the same query on the same data runs in 40 seconds instead of 12 minutes, and why the answer has almost nothing to do with Spark.